Good morning, everyone. Welcome to the third day of the SDL workshop. This morning's presentations are going to be focused on our AI testbed, as well as workflows and how to do workflows on Polaris. Both talks have some hands-on components, though I understand that the AI testbed hands-on components are going to be getting support in the afternoon from this team. Zhen, please take it away.
Okay, thank you. Thank you for the introduction and welcome to the ALCF simulation data and learning workshop. So this talk is about the AI testbed, and we also have some hands-on section in the afternoon. So the title of this talk is the introduction of the AI testbed and the hands-on. So we will introduce something about the background of the AI testbed and some software, hardware stacks, and we will use for the hands-on section, we will use the machine learning models to run it on the AI accelerators. And here is our team. So we did a lot of efforts on the AI testbed, and also we have a lot of progress, and I will introduce them in the next slides. And here I will introduce the background of this work. So as we know, the scientific machine learning is become more and more popular, and we have a lot of simulation and surrogate models. So by using these models, we can replace or guard the simulations with AI-driven surrogate models, which means we can replace some part of the HPC applications and to use the AI-driven models to accelerate the existing HPC applications. And also we have some data-driven models. We can use the data to build the models without simulations. So which means we do not need to use the simulations code, and by using the machine learning based code to make the simulations run faster. And we also have some core designs of the experiments, which we call it AI-driven experiments. So on the one hand, we use the simulations, and on the other hand, we use the AI-driven models to make the simulations run faster. So we have some examples to show how can we use that. So the first one is the protein folding examples. In these applications, we use the machine learning based models to predict the protein shape based on the input of the sequence of the RNA. So and the second one is the bragging peaks, which we can use the machine learning based models to predict the particles and type based on the shapes of the different kind of the particles. And we also have the third examples is the galaxy classifications, which we can use the machine learning based model to classify different type of the particles in the glass. And the design of the infrastructure to facilitate and accelerate the AI for the science applications. So the goal is we want to make the using the machine learning to make the HPC applications run faster. And I will introduce the hardware and the facilities in our system. This is the map of our lab, and we have the different kind of the computing facilities. And as we know, we have the Aurora which has a lot of the NVIDIA A100 GPUs, and we also have the SATA GPU and something like that. We have the GPU based computing systems, and on the other side, we have the AI accelerators based computing facility. And for the AI accelerators, we have the AI accelerators is different. So we have the different kind of the AI accelerators. Currently, we have 5 kind of AI accelerators that we can use, and based on this computing facilities, we can make the simulations and the data-driven models to run based on them. and to make the best use of our system, either on the GPU-based systems and the AI accelerators-based systems. And the goal of the ALCF AI activities at Argonne is we would like to accelerate the science by effectively coupling the AI systems and on the very large supercomputers and the experimental facilities. So the goal is the first goal is we want to build the maturity of the software and the hardware for science. And we also want to build the ability to scale the hardware and integrate with the facilities, which means if you have some HPC applications, we want to make them run. We would like to run the HPC applications on our systems and to make the best use of our facilities. And we also want, and the third goal is we want to make the applications at a scale to science, which means because we have the large scale of the system, so and based on this way, we want to get a very high speed up when the loads of the computing loads increases, and we can also get better performance based on that on the large scale. And here I will introduce something about our systems, the ALCF AI Testbed. So this is the link of is the website of our systems, and if you want to get more information of our systems, you are free to access this link. And currently we have 5 kind of the systems to use, the AI accelerators to use, and the first 2 is the public access, so which is the Cerebras and the Sambanova system. The 2 systems are designed for the DNA training, but then they can also do some inference. And the second 2 called the Graph Core and the Hambala, which were designed for the training and the inference. And the last one is
Did we lose him?
That's what I was going to ask. I think we did. We see your screen again.
okay. Sorry for the network issues. So the network is not stable. So just we talk about 5 kind of the accelerators. The first 4 are designed for the training and the inference. The last one is designed for the inference only. And for the AI testbed, the infrastructure of the next generation's machines, which we call the AI testbed, is customized for the deep learning networks and the AI applications. And we also provide a platform to evaluate the usability and the performance of the machine learning-based HPC applications running on those applications. So currently we already try a lot of applications based on these systems, and we also have some micro benchmarks to test the performance of those those systems as well. And the goal is to have the better understanding how to integrate the AI accelerators with ALCF existing and the upcoming supercomputings to accelerate the science insight. So, and currently we already run a lot of applications, the scientific applications on those systems, and we already have some performance speed ups compared with the A100 GPU. And the next, I will introduce what's the difference between the traditional GPU and the AI accelerators. Well, so I choose one of the AI accelerators as example, the Sambanova accelerators as examples, which is the Dataflow architecture. So, and we have the examples to show what's the difference between the GPU and the Dataflow processor. And this is the very simple convolution graph. We have some input, and we also have the 2 convolution layers, and we also have the 1 pooling layer, and we have the 1 normalization layer and some operations. So for the traditional GPU accelerators, each kernel is launched onto the device totally, and the bottleneck including the memory bandwidth and the kernel launch latency. And we can see here each operations will run on the whole device, and the different layers transfer the data by using the global memory. And if we use the Dataflow AI accelerators, and we can see the kernels are mapped to different part of these accelerators. As we can see in the different colors and on this chip, and the different kernels mapped to the different part of the AI accelerators, and the data flow on chips between them can reduce the memory traffic. So as we can see, the data transfer between the different part of on this chip, and because they can provide very high communications between different chip between the parts, so we can get the better performance between by using the on-chip data transfer. So this is the difference between the GPU and the AI accelerators. So based on this different design, we could get better performance. And I will show more details with the AI accelerators and the traditional A100 GPU. The last column is the traditional A100 GPU, and the 5 column are our AI accelerators. So as we can see, the NVIDIA A100 GPU has around 7,000 CUDA cores, and we can see the different kind of the AI accelerators also have the different numbers of cores, and especially for the servers, they have 900,000 cores. This is much larger compared with the A100 GPU. And as we compare to the on-chip memory, the A100 has 40 megabytes L2 memory, and for the different kind of the AI accelerators, they have much larger on-chip memory, so which can provide much better data locality and much higher memory bandwidth. Especially for the server CS2, they can provide 40 gigabytes on-chip memory, and for the Groq core, they can almost provide 1 gigabytes memory, on-chip memory. So this is much larger compared with the A100 GPU, which can only have 40 megabytes L2 on-chip memory. And also we have a different system size. For the A100, we currently have the Zeta GPU, which one node has 8 A100 GPUs, and for the parallels, one node we have the 4 GPUs, and for the Cerebrus, we have 2 nodes, and each node has 8 cards. And for the Sambanovas, we currently we have 2 nodes, and each node has 8 cards per node. And for the Groq card, we have 4 nodes, and each node has 8 cards. And for the graph core, we have 1 node, and each node has 8 cards. And for Habana, we have 2 nodes, and each node have 8 cards. So, and this is the system side of the AI accelerators, and they also can provide different peak performance. For the A100, they have the 2 kind of the precision they can support. The first one is the single precision. They can support 156 T-flops for the single precision, and also they can also support half precisions, and it can provide around 300 T-flops on 1 card. And also the different kind of the AI accelerators can also provide different performance based on different data formats, and most of them can support half precisions as well. And for the Cerebrus, they can provide the 5,000 around 5,000 T-flops. And for the different cards, they can also provide hundreds of the T-flops for the single precisions. It will also compatible with the A100 GPU, and the Cerebrus is much larger compared with the A100 GPU. And for the software part, software stack support, the NVIDIA A100 can provide the TensorFlow and PyTorch and some popular deep learning frameworks. And the AI accelerators can also provide the software support, such as the TensorFlow and PyTorch, and they can also provide some specific software to get the best performance of the AI accelerators. And for the internet network, the NVIDIA use the NVLink to communicate with each others in one node and between different nodes. And for the AI accelerators, they use the InfiniBand or some specific networks to provide such communications. And this is the details of the AI accelerators. So next, I will introduce some applications we already run on the AI accelerators, and I will show some performance difference between them. So currently, we already migrate the cancer drugs applications to the AI accelerators, and also these applications use the image and networks to predict what kind of the drugs can be used for the cancer. And the second one is the Bracken peaks, which is used to predict the particles, different kind of particles. And the third one is reactor operations, and the last one is the protein folding, which are used to predict the shape of the protein. And we have more applications is ongoing, and they are trying to use the AI accelerators. And I will introduce one examples to show the performance difference between the GPU and the AI accelerator. And we choose the cosmic taggers as examples, and we also choose the Sambanova datascale accelerators as examples to show what's the difference between the A100 GPUs and the Sambanova, which is one of the accelerators. So the goal of this application is to use the image segmentation task for the liquid argon time projection chamber detector to classify each input pixel into 3 kinds of classes: the cosmic, moon, and the background. So, this application is a high energy particle physics domain applications, which would like to deal with the detecting the different kind of the particles. And then the goal is to classify different particles to separate the different 3 kind of different particles. And these applications use multiple 2D particles as examples, and it has some different kind of the convolution layers, and then they also have some kind of the downsampling layers for this network. This models use ResNet models, which is modified by the UNet models. The UNet models is commonly used by the computer vision models across different domains, but we change a little bit and make the ResNet models for these applications. And the challenge here is the model size is dependent on the image size. Currently, one needed to downsampling to the image to run on the GPU system because of the limited memory size of the GPU. And we will show some performance difference between the GPU and the Sambanova RDU. So this is the training example. This is the result of the training testing result and the training result. And the orange line is the Sambanova result, and the green line is the GPU result. And we can see they use different image size because of the memory size. So because of the Sambanova has a larger memory size, so the Sambanova can use the bigger image size, but because of the GPU has a limited memory size, so they can use the smaller image size. As we can see for the testing data, the Sambanova can get a better performance, and for the training data, they can also get a better accuracy compared with the GPU. So the Sambanova RDU are able to accommodate a larger image size and achieve a higher accuracy, both on the training data size and the testing data size. And this work was also published there in the computing, in the science and engineering. And if you want to know more details, you can check these papers as well. And we also have some results with the inference on Groq, which is also one of the accelerators, and this accelerator is designed for the inference. As we can see, we use the forecasting plasma instability in tokamak, these applications. As we can see, we compile the throughput. The y-axis is the different kind of the hardware configurations, and the y-axis is the throughput. The higher is better, and compare with the A100, which use one batch size, which use the batch size of 1, and we can see the Groq can get much larger performance speed up compared with the A100. And for the batch size of 128, we can get a higher performance throughput compared with the A100 GPU. And for the throughput, so for the throughput part, the throughput is much smaller when we run the applications on Groq. And we also did the application for the candidate drugs molecular screening applications on the Groq. As we can see, if we use the Groq accelerators, we can get around 300 speed ups compared with the V100, and we can also get 150 speed up compared with the A100 GPU. So the results show that the Groq chips for science inference can provide the much higher throughput and a much smaller latency compared with the A100 GPU. So which means we can get better performance on that. So, and the next I will introduce two kind of the AI accelerators as well. And this systems is public to the is available for the public access. So the first one is the Sambanova systems, we introduce this system from two parts. The first part is the hardware part, and the second one is the software part. So begin to jump into the hardware part. I will introduce the motivations of the hardware design. So currently, for the deep learning training, we have a different parallel patterns. So as we can see, we have some map parallel pattern, which is the elements-wise functions and we also have a zip and function, which is also a element-wise functions to make a collection of different elements. And we also have a reduce function, which want to combine all of the elements together with one single result. And we also have a flat mapping operations, which is elements-wise functions to map different elements to multiple other nodes. And we also have the group by functions, which want to group elements into blocks based on the one keys. And so currently we have a different kind of the parallel patterns, and we would like to run the different kind of patterns on a fixed hardware design. So it's difficult to get a very high performance with a fixed hardware design. So the Sambanova proposed the reconfigurable Dataflow architectures to solve this bottleneck. So they propose a reconfigurable hardware design for the as shown here. So as we can see on the right side, we can see they have the different kind of the units. This is the memory unit, and this is the computer unit, and then they can collect it by the switch. And based on that, you can map your workload to different part of the unit to get different kind of performance. And also, I will introduce the hardware details of this design and this chip. This chip can provide around 250 T-flops performance, peak performance, and then they also have the hundreds megabytes memory on chip memory, and then they also can have some direct interface to a larger off-chip memories as well. And we call it SN10 RDU. This is the world's first reconfigurable Dataflow unit. And as I will take examples to show how can they map the applications to the real hardware. So as we can see, we have a simple convolution networks to run, and how to map so as we can see, they map the different kind of the part, such as convolution part layers, to different part of this chip, and the data transfer between different part of the layers, and finally they can get the result. So they do not need to access the off-chip memory, and just by using the on-chip memory. So by using the on-chip memory, they can get the better memory bandwidth and get a lower memory latency based on this design. So they also consider the scalability of the performance for the training and the inference. They provide different configurations of the hardware. The quarter racks will include one card which include eight SN10 chips for the one node, and then for the half rack they provide two nodes, and each node has 8 SN10, and for the full rack they provide four nodes, and each node has 8 SN10s, and for the memory size, they can provide the more than 90 times more memory compared with the DGX A100 GPU, and then they also provide a very high. So how to connect the different RDU and loads between them? So they provided two kind of the networks between in node and between different nodes, and as we can see, we have the different RDU in a single node. So they provided the RDU connect to connect the different RDU, and the bandwidth is around 100 gigabytes per second. And between different nodes, they provide the RDU director, which has 25 gigabytes to 50 gigabytes per second to jump to the other nodes. And this is a network design for this hardware. And next, I will introduce what's the software design of the Sambanova. And for the software designs, as we can see, they provide different kind of layers for the software stacks to get the optimizations which want to deliver the best performance of the models and the hardwares. So as we can see, if we have the one models, the algorithm layers will analyze the models to try different different positions and the different sparsity, and also they will try different kind of the compressions techniques to make the models much lightweight. And the compiler layers want to also will analyze the models, and they will try to use the global data flow, and they also have some memory optimizations to try to have the best map of between the algorithm and the hardware. And for the architectures, they will have the different hierarchical computer and the reconfigurable memory units, and they also have the data flow optimized communications in one node and between different nodes. And for the hardware design, the VLSI will provide very high performance implementations. And this is the 4 layers of the software design. But for the users, you do not need to consider anything about the code beside the models. So for the users, you just need to write some code such as PyTorch code and use the interface to write some graphs to use the software stacks. So which means you just need to write some PyTorch code to use this hardware. And if you write some models based on the PyTorch, the machine learning data flow graph analysis will analyze your models and build them to different kind of operations, such as they have some customized operations and some machine learning based operations. And the optimizer and the layout opponent will analyze your operations and build them to have the best optimization and the layout, memory layout. And after that, then they will have the runtime component to run their operations to the real hardware. So, and for the optimizations, they have the model parallel, data parallel, and the tiny streaming. That is the pipelining and the operation parallel to make the best use of the optimizations. But the users do not need to consider the optimizations because they do the optimizations automatically on the backend. And I will introduce examples to show how to run the code on the RDU. And this is the examples of a very simple convolution that works. And for the traditional GPUs, they will run different kind of the operations on the whole process, and they use the use the global memory to change the data between different layers. But for the RDU, they map the different kind of convolution layers and the normalization sum operations to different part of on this chip, and then the data flow compilers will map the operations to the different part of the chip, and the program will have the communications between them automatically, so the users do not need to consider what happens in this chip, and just need to write this code based on the PyTorch interface. And then the Sambanova eliminates the overhead and maximizes the utilizations of the hardware. And next step, we introduce a little bit about the precisions supported on the Sambanova. So currently we have the two kinds of the data format supported by the Sambanova. The first one is the single precision. This is very common for the deep learning training. So, and it also the default format for the deep learning training. So, and for the BFC and for the half precision format, the Sambanova can provide reduce the precisions, which is the half precisions that have the same dynamic range as the single precision, but it has less accuracy, and then amounted to matching the size of the single precision component field to the 8 bits, and shrinking the size of the single precisions functions field down to 7 bits. And with the BF60, the Sambanova can provide a higher training throughput. And the next I will introduce the hardware part of the Cerebras. This is the second AI accelerators and it's also publicly accessible for the users. And if you want to see more details of this AI accelerators, you are good to to access the white paper of the Cerebras systems as well. And I will introduce the motivations of the hardware design for the Cerebras. And for the traditional GPU approach, they have some bottlenecks. The first one is they have a small size, less than 10% size used for the deep learnings, and more than 90% size used for the graphics, such as some engine and the shadow texture map and the thread and the instruction control, such as here they have the different part not only used for the deep learning training, and also the memory is far from the graph core. They have a limited on-chip memory, such as we show in this figure is the L2 cache is too small, and they also have the cache-based memory hierarchy. So they have the different cache hierarchy. So they have the L2 and the L1 memory hierarchy, and as well, and the graph core not built for communications. So because they have for the on-chip memory, they have the low bandwidth and the very small size of the on-chip memory, and for the off-chip memory, they have the even lower bandwidth, and they use the PCIe and the Emani code to communicate with different memories. And for the design of the dense matrix operations, the sparsity is not fully supported for different kind of the networks, and they also implemented as a CPU core processor. So to solve those bottlenecks of the existing GPU approach, the Cerebras propose the CS2 as the solutions. So as we can see, the CS2 is much bigger compared with the largest GPU from the size, and they also provide the very large number of the AI optimized cores, and they also have the larger on-chip memory as well, and then they can provide very high memory bandwidth, and the fabric bandwidth as well, and then they use the TMSC process. And I will introduce the hardware of the CS2 from two ways. The first way is the AI optimized compute. So this is the compute, the micro architectures of the AI accelerators. So they have the fully programmed cores and the machine learning optimized extensions, so which can run the access metric, logistic, and the load store and the branch operations on this chip. And then they also have the Dataflow architecture optimized for the sparse dynamic workload. So based on this design, they can have the high performance for the sparse and the dynamic workloads, and we can run the sparse neural network and some dynamic workloads on this chip with very high efficiency. And for the memory side, as we can see, the traditional memory architectures share the memory, which is far from the compute. As we can see, for the GPU's design, they have some cores, and the memory is a little bit far from the cores. And the right answer is distributed high performance on-chip memory. As we can see here, the memory is distributed across different cores, and each core can access the memory is very near to the cores, and which can provide higher throughput and lower latency as well. And for the communications, the Cerebrus can have the AI optimized communications, which can provide high bandwidth, low latency, and a cluster scale networking on chip. And it also is full configurable to users to some specific topologies, which means if you have some specific topologies of your network design, they also have some specific communications topologies are designed for your networks. And this is the details of the difference between the A100 and the Cerebrus CS2. And to compare with the A100 GPUs, the Cerebrus has 50 times its larger chip size compared with the A100 GPU, and then it has 100 times larger cores compared with the A100 GPU, and then it has a 1,000 larger on-chip memory compared with the A100 GPU, and then they also have the around 10,000 times memory bandwidth compared with the A100 GPU, and then they also have around 45,000 times fabric bandwidth compared with the A100 GPUs. Based on the hardware design of the CS2, they can provide a higher performance for the deep learning training and as well. And to make the best use of the hardware design, they also provide the software stacks for the users. And as we can see here, in the Cerebrus software stack has the different kinds of layers to provide to get the high efficiency of the hardware. So the first layer is the frameworks. They also can provide some TensorFlow, PyTorch, the deep learning frameworks to the users. And the first step to extract the operations from the existing graph and match the different the operations to the different kernels. And the third one is to place the graph to the real hardware, and then the last one is to create an executable output that can be loaded to run on the Cerebrus CS2. And then they provide the familiar machine learning frameworks as well for the users, and such as TensorFlow and PyTorch. And the users starts as a user by developing the machine learning models based on those frameworks, and the Cerebras integrates the popular machine learning frameworks, so the researchers can write the code by using the familiar tools, by using the popular machine learning frameworks as well. And for on the back end, the Cerebras has a LAIR. This is the standard input to the Cerebras software stacks. So they will extract the nearly algebra graph representations of the models from the machine learning frameworks to the Cerebras. So this is the workflow of this process, and the users will write some code based on the TensorFlow and PyTorch, and then the compilers will extract the framework operations based on the models, and the Cerebras will map the different operations together and build the operations to LAIR, and after that they will run the LAIR on the counter hardware. And I will also introduce the teams of our AI Testbed community engagement. So we have a large team supporting the AI accelerators, either on the software part and the hardware part, and we also did a lot of things on the AI accelerators, such as we have the Sambanova AI training workshop, and we also have the aspect hardware and the software architecture day to show the architectures of the Cerebras and the Sambanova. And we also have this ARCF AI for Science training series for the students, and we also have the Cerebras CO2 training workshop, and for the academia part, we have the SC 22 tutorials on this year, and the title of the programming AI accelerators for science and computing, and we were present in these tutorials with Cerebras in Habana and the Groq and the Sambanova teams. And currently our system is public accessible, and if you want to access our systems, you can just apply for the director's discriminatory allocations award to access our systems. So you can just request the allocation forms and to connect with us to get the access to the AI accelerators. And we also have the Testbeds user guide to help you to how to access the systems. And I will introduce what we will do on the hands-on section for the Sambanova and the Cerebras. And for the hands-on section, we will use the BERT language models on hands-on section as our examples. And then this is the BERT is a transformer-based machine learning techniques models for the natural language processing pre-trained models developed by the Google. And the original English language BERT has two models. The first one is BERT base, which has 12 encoders, and then the second one is the BERT large, which has 24 encoders. And this is the architecture of the BERT large BERT models, and we will select the BERT large as our models for the hands-on section. And it will be easy to use the systems either for the Sambanova and the Cerebras. And for the Sambanova hardware, the first step is to log into the Sambanova and by using your ARCF user ID, and also you can jump to the one Sambanova loads. And the second step is to set up your SDK, the software environment. And the third step is to copy the scripts to your local directory. And then the third step to run the directory the scripts will include the training and the inference as well. And for the server bus, and the first is the step is similar. So the first step is jumping to the use the ALCF user ID to jump to the server bus nodes, and the next to jump to the one server bus nodes. And the second step is to copy the scripts and then modify the data directory to in the configuration file. And the third step is to run the scripts by our provided the comments. And thanks for everyone.